My name is Peter Burris. I'm the Chief Research Officer for SiliconANGLE and run the Wikibon business. Wikibon is a community dedicated to advising users what technologies to use, how to use them, and how to get the most out of them. We have a number of different perspectives, but what you're going to see over the course of the next hour, hour and a half is some great panelists, including, or some great presentations. So we've got someone here from NYU, the Center for Data Science. We've got someone here from Lumiata to talk about the relationship between healthcare and deep learning. And we've got a couple of panels. We'll take a short break and we'll fire up the first panel, and the first panel is going to focus on kind of the evolving landscape of the relationship between software, data, deep learning, and business. And that's going to be hosted by George Gilbert, and then I'll lead a panel that dives specifically into some of the technologies that are going to make that possible, including database and some of the other technologies. So we've got a lot to do over the course of the next hour and a half. We're very, very thankful here at theCUBE SiliconANGLE for the support of NVIDIA in helping set that up. Jim McClure, why don't you stand up? So if anybody wants to talk to some of the great things that NVIDIA's got going on, Jim can point you to the right person in talking about the increasingly powerful relationship between GPUs and some of these new technologies. All right, so let me set the context over the course of about 2 minutes. And if somebody wants to time me, go for it. So here's the context. Every business is trying to evolve digital capabilities that will differentiate them in the marketplace. They're doing so for a number of reasons. The top reason, of course, is that customers are not just requesting, but demanding new styles of digital interaction that make the customer a better decision maker, that allow the customer to get more value out of products and services, and ultimately make the customers look more like heroes in their organizations. So this crucial relationship between digital business and competition looking forward is starting to unfold across all corporations of all sizes. Now, a lot of analysts like myself talk about that relationship, but they don't really get down to its core. What we think the core of this relationship is data. We define digital business following what Peter Drucker famously said a number of years ago as the use of data to differentially create and sustain customers. We are now in an era where data is becoming acknowledged as a crucial differentiating asset in business. Now, to make that real, you have to do a better job of capturing it, you have to do a better job of turning it into models and insights, and you have to do a better job of then ensuring that that data enacts change in front of customers and in front of businesses as well. Tonight we're going to focus our attention mainly on that crucial challenge of taking data from large numbers of inputs and turning it into models that have powerful implications for how businesses behave. Now, there also will be opportunities to touch upon other things, but that's kind of the centerpiece of what we're talking about. The emerging role of data as a way of generating models that enact crucial business change and generate superior customer experience and superior business. I'm going to start off by introducing Claudio Silva. Claudio, are you here? Claudio is the director of the Center of Data Science at NYU. He's done some phenomenal work with Major League Baseball, a number of others, and Claudio is going to come on up and introduce and spend some time about his research and his learnings. We're not going to take questions for either of the two keynotes, but we will during the panel. So Claudia, please.
I'd like to thank Peter, Jim, and Renee for making this happen. So I know I have 15 minutes, so I will try to, I think that this is not my computer. I was like, okay. So, okay. The data point of one, I'm like, I'm sorry, I need my computer. Thank you. All right. So what I will try to do over the next 15 minutes is to show you some sample of the work we've been doing on data analytics on GPUs. In particular, our lab has two main focus areas, and one of them is urban computing, and the other one is sports. I'm really passionate about those two things, as you're going to see. And what I'm reporting on here is actually just a small slice, tiny little slice of work done by a lot of people. And they're listed on kind of like, some of them are listed in this first slide, some people are listed on the second slide. And we're so fortunate to have funding from a number of organizations, including NVIDIA, that donated a DGX-1 to NYU. It was the first one on the East Coast. And we are trying very hard to make it, busy every minute. Okay, so first, urban data analysis. It's funny even having this slide when you're giving a talk in New York City because it's obvious, right? So cities are where things are happening, right? I don't know how many of you know, but 50% of the population now lives in cities, and we are going to a point where 70% of the population is going to be in cities by 2050. And so much happens in cities. So understanding, finding some way to, make cities more efficient and sustainable and improve the life of its residents is extremely important. And computing is an aspect that you can actually do this. I'm not going to dwell this on too much because I only have 15 minutes. So I'm going to jump right into a particular application where we have a super interesting spatial temporal data set and that we need to do analytics on it, okay? So what's that data set, right? So we see taxis everywhere in New York, right? And it might, I don't know, at this point it might not be a surprise to you, but actually all the taxi trips in New York is available, publicly, okay? So this wasn't the case 5 years ago, but now it's the case. You can just go on the website and can download this. So there's about almost 200 million trips a year, right? And this tells you all kinds of interesting things about the city. So here is actually a plot. Each one of these plots you see here is the quantity of trips of cabs throughout a whole year, so 2011 and 2012. And there's all kinds of interesting things you can see here. You can see kind of like this, as people go to summer, this drop over August. You can see the beginning of school happen. You can see weather events and other kinds of events. You can see Thanksgiving. It's actually amazing. Later, when these slides are available to you, you can actually check out and find things and find Valentine's Day on this data, right? So there's all kinds. You can imagine that these kinds of data sets that track enough of the city, right, over space and time, as basically sensors, right? This is just there, and you can find interesting stuff on the data, right? So you can look at, where the popular night spots, you can actually find that on this data. So what's the challenge here, right? So this is a big data set. It has time components like the one I'm showing on top, has space components like I'm showing on the bottom here. How do you find anything on this data at all, right? And then also the fact that this is large. So, a typical data set that we would use in our lab now would have 1 billion taxi trips, right? So it's 1 billion with a B, and this actually, this data, even simple things. So I'm going to cover the most simple, probably the simplest application we've done in our lab that is just querying this data, right? This was our very first paper on this almost like 5 years ago, and it was on this tool called TaxiViz. You can get this on GitHub. As many of our tools, they're just open source, socially available. So I'm going to actually jump over a number of the technical details here, but one of the ideas of TaxiViz was actually just to democratize this data, right? So to go from a point where the only people that could reuse this data effectively are data scientists, to a point where domain scientists and actually people at the New York City agencies could use this. Okay, so we created, instead of you using SQL, you kind of like can use, visual language for this. We came up with that. And one of the things that is very important, and I'm just playing this video really quickly here, is that everything has to happen interactively. That is kind of like, where I wanted to go is everything has to happen interactively here. But then you run into a problem. If you try to do this with traditional databases, you try, let's say initially we tried something like SQLite, okay? Even for just 1 year's worth of data, small queries would take 8 seconds, And slightly larger queries would take on the order of minutes, right? When you went to Postgres that has actually a GIS extension, you would still be at the multiple seconds per query, actually at even like half a minute, right? And what we really need, and our initial solution was based on a clever CPU solution, is you need sub-second responses, right? And this is actually where what we find time and again, and I mean this is going to be a theme of this lecture here, or this short talk, that you get so much faster when you actually carefully think through these problems in GPUs, okay? Not going to be able to explain to you the technical details, but I guess that the important number here is, you might not believe this slide, right? Actually, the reviewers didn't believe it either initially, right? So most of but the code is on GitHub. Harish is right there, so you can check up his code. You get speed ups on the order of over 6,000, right? Compared to GIS extensions on CPUs. So there is actually a whole reasons for this. We can talk about this during the panel, okay? But it's really interesting, right? Part of this is that the GPUs have just been constructed for this, right? They from purpose, they're great with geometry, they're great with time, right? So it's very natural for these different data types we are using here to be using them for this. But we need clever solutions too. It's not just using the GPU, right? So I want to now show you, how do we actually put all this together? So I'll show you a really short video of a project that is actually being used to change the way that we do things here in New York. So just really quick, that's not the one. It's, oops. It's this other, oops, it's YouTube. Oh yeah. This has sound. I need sound on the laptop sound. The laptop is not muted. It should go out of the HDMI actually, but okay. So the problem is once you put the HDMI. Okay, I think I actually know how. We couldn't test this out before because let's actually do this sound.
New York City, it's been estimated
Growing
that
up, you likely learned about the primary colors
or
red, yellow, and blue,
the
and their
garbage
respective
truck.
complementary colors. But things are more complicated
be
when you
really
consider
affected
that the
by
primary colors in the
sirens
picture
here.
are magenta,
It makes it
yellow,
harder
and
to kind
cyan,
of
or that the screen you're
focus,
watching
'cause
this
there
on
is just
uses
so
red,
much
green, and
background
blue.
noise to block
These are
out.
different color models where
Noise
RGB
pollution is
additive,
really
meaning
one
the
of the
mixing of different
topmost-
lights of color create new colors, while the other two are subtractive models and absorb different wavelengths of light. For example, when you hold a yellow object in real life, it's actually absorbing every wavelength except yellow.
The other
that
one
yellow
is
light
not-
bounces
I'm
back
not playing
and
the
hits
other
your
one.
eyes. But when you look at this
I'm not
yellow
playing the
object-
other one. I mean, so this is not coming out of my laptop. So we have to choose the right source here. Okay, maybe I give up on this. It's just kind of cool because this has a very non-trivial use of deep learning. So okay. So let me put it this way: we don't have the sound. We did these sensors that we designed, and then right here, this is actually a deep neural network that, believe it or not, we are playing sounds and it's saying what it is. Okay. I can just point you to the video and you can see it's a cool video. So this would be like you show the drilling sound and it says like this is drilling, you know. So okay. I have no other sound that I need on any one of the rest of my talk. Okay. So, but I think that the point here is that this kind of technology and these GPUs are being used, in practice, and we are actually trying to expand this. And one of the things that is very unique about this is that we kind of like, as you're going to see, kind of like the ability to run this multimedia data through this new processing unit is really enabling us to do things that we couldn't otherwise do. So another thing is, for the past 4 years, I don't know how many people here, sometimes I talk to people that know what StatCast is. So baseball, okay? So we wanted to have better ways to track the players and to be able to compute the statistics. So one of the things that we've been working on together with MLB.com, I've been working on this for about 4 years now, is on trying to design systems that are able to automatically compute statistics from directly from player data, right? So we had a preliminary paper about 3 years ago, and this is actually one of our early videos, but it actually highlights this really well. So what you see here is you see the virtual players. They're kind of like the shadow of the real players, right? And you see the real players going, and you see this noisy data that is going through, and we are actually doing this augmented reality app, right? That is kind of like also rendering this on top of each other, right? Okay, so you can just imagine all kinds of processing that we have to do this. It goes all the way from calibrating cameras to views that you haven't seen, to tracking players and showing what they're going, and then also all the data cleanup. And it's actually on purpose that we are showing you the raw data there, because we want to show that it actually is the data that comes through real time in the system, right? So the bottom line is that this is actually a super complicated system now that actually the BIM guys did, where they have stuff installed in the stadium. The data actually gets put on the cloud. It eventually makes into the code that Carlos Dietrich and I wrote, that then consolidates all this stuff and puts it back in the database, and then we can use it for interesting metrics, right? I'm not going to give this demo now because we don't have the time. I have it on my laptop. Actually, I have it live here. But this can actually access the kind of like the data as it's happening on a game. It's like we actually have this limit of like 12-second delay. We make sure that no processing takes more than that. But I want to go into beyond what we're able to do now and what we're actually now kind of like trying to push the limit. So one of the things we're trying to do is trying to use deep neural networks for analyzing, player behavior, and for trying to understand, different processes that are helping on the field. So one of the first things we try to do, and we are trying to, one of the big challenges we have when we apply deep neural networks is that you need training data, right? You need lots of training data. So one of the ways we got around this, and this was work with Rodrigo, is that, we can actually generate the training data by the fact that we can generate virtual models of the data. So we can basically use renderings as the real data. And this is a little bit tricky. I don't have time to discuss this here. But then in the end, it actually works fairly well. So once you do this, you generate virtual models that you can play, right? You can start to do this kind of stuff. So with this, we're actually trying to understand things like player behavior. So if you think of the player as they are moving, okay, right now the systems that we have, they can track the center of a mass, the projected center of mass of the player, okay? And with this, you get curves like the one that you see on the left there. What that is the Y signal from the player as they leave the plate moving forward. So you see kind of like when the pitch happens, it goes down, right? Okay, right? And then you can see kind of like, because we have this data over multiple years now, and for every single pitch, we can see the behavior of the different players. We can compare players. We can see how they move. It's still one of the problems is that we are able to do what I still call very rough analysis. We can separate, for instance, a wind up from a stretch from this, and that's what this graph is showing, right? But we actually cannot tell exactly what the style of the player is. We cannot do things like saying maybe they're going to get they're going to get injury, right? So this is actually something that we are in the process of applying the same kinds of techniques, a fancier version actually, of what you saw in Rodrigo's work to this kind of video data. So this is going to go in terabytes and terabytes and hundreds of terabytes of video, right? And we're going to have to tunnel that through the GX1 and see what we get there, right? And then we also been working on how do we do this for other sports. So we've been working with hockey data now. Anyway, I want to thank all of you for coming to this lighting talk, and also my lab. You know, I'm part of this lab with 5 faculty, and we are actually now, last I heard, we're like about 70 people, and it's been wonderful to do that. So thank you. We are not taking any questions now, but I'll be happy to talk to you later if you're interested.
Why wait for the future?
Hi everybody, Jeff Frick here with theCUBE. We are on the ground in Dearborn, Michigan at a huge Ford event. It's called #FordTrends. It's a 2-day event where Ford is bringing in kind of social media people from all over the world to really talk about disruption. It's all about disruption, mobility, sometimes talked about as autonomous vehicles, but really it's a 2-day slate full of a lot of key executives from the Ford team. We got to go out and drive on the autonomous vehicles, but really again talking about disruption.
Today. Before I start, I want to ask a question. How many people here feel all their data is being put to use in healthcare? Exactly. I mean, not a surprise, right? But the question is why? Why is that the case? Especially now that we are collecting literally hundreds of times the amount of data that we were 10 years ago. Why is that data not being put to use? And fundamentally, it's because it's a scale problem. We do not have the time or the resources for people to review all the data over multiple years over very complex data for each one of us in a way that can scale. And so what I'm here to hopefully talk to you about today is a bit about deep learning, a bit about AI, but fundamentally, how do we unpack AI for healthcare? To give you a feel of the challenges that happen to be, some of the ways we here at Lumiata are trying to address those challenges, but obviously excited by the conversations afterwards. So I'm sure all of us can feel a very lack of control whenever we engage with the healthcare system. And for better or for worse, actually that's true of everybody. Payers or health risk bearers also feel the same way, and so do providers. We're all struggling to make sense of all this health data. And to say the least, our health is complex. Each one of us is made up of some 37 plus trillion cells, and lots of stuff are going on. So even if you're sitting down thinking you're not doing any work, you actually are. Don't worry, lots of stuff is going on. But the thing is, we have no control because we have no visibility. Rather, tomorrow is fundamentally a black box to us in terms of our health. And that's actually the whole problem. Fundamentally, I always say this is part of the company. You can't manage what you can't predict. And so really our focus is here is to give us the tools to be able to predict so we can actually manage effectively. And so as a result of this inability to protect, we really cannot coordinate. We can't actually communicate effectively. And so what we see is what we have, higher and higher costs with little improvement in health outcomes. And the whole focus where our hope is that through AI, we can actually surmount these challenges and actually make a difference. So in reality, there is an opportunity with the advent of electronic health record data, with labs, with genetics, with sensors and wearables. We are basically generating and capturing huge volumes of data. And through AI, through deep learning, and through these new mechanisms that we have, there is actually an opportunity to actually make a difference. But the reality is healthcare data is perhaps one of the most complicated data sets out there. A lot of data is very tall, a limited number of variables, but huge amounts of it. The difference of healthcare fundamentally is actually, it's very wide and very deep. So for an individual, you literally could have thousands upon thousands of different variables, and it's very different amongst each person. So you have very sparse, but very high dimensionality data. And it's multifaceted and interacts in very complex ways. And the thing is, currently today, we're still dealing with this and not necessarily the best thing. Best way is leveraging, SQL databases and the rest. We really need to move forward. And that's what's really exciting about things like deep learning and GPUs. It finally is providing us these skills and tool sets that we need to really make a difference. And we've seen this in other places. We see Google now. It helps us figure out, should I go on the 101 or 280 for those who are back in the Bay Area. Amazon for what I may be excited by purchasing. But the question is, why aren't we seeing this in healthcare? And the interesting thing is healthcare and AI is fundamentally best poised to solve this problem, because what it's fundamentally doing is being able to surface the signals from the noise. And really the idea at the end of the day is to give us a sense of control, to allow us to manage, from automated information processing to very precise disease management, to basically really enabling us to, when we're actually engaging with another human being, to be able to get the most out of it. And to be able to go ahead and therefore not feel silly for asking the same question 10 times in a row because we're not feeling well. And so the question we sort of posed ourselves was, what if we could use AI to predict the future? Could we actually really bend the cost curve? Could we actually really improve outcomes? Could we actually learn and understand what works for whom and why? And so the question we asked ourselves is, can we build those machine-based systems that allow us to surpass our limits of precision and timeliness so that we can actually drive into a world of truly personalized care? So it requires a lot of domain expertise. A lot of people say deep learning. It's not a magic box. It takes a lot of work to really understand how to deal with the data. And especially when we're talking about clinical data, how is it we can really take the combination of clinicians and data scientists together? It really requires the ability to understand how to deal with these highly complex data, right? I mean, it really is truly of high dimensionality. And frankly, we're now starting to deal with large volumes, right? How do we terabytes and petabytes of data about this, especially when it's noisy, it's dirty, it's fragmented, it's siloed, huge number of multiple challenges. So unless you are very familiar and understand how to deal with that, you are not going to be able to make use of it. And frankly, the infrastructure, how do we process 2 million people in 2 hours? How do we get the stream of data, truly be able to process things in the streaming environment? So leveraging things like Spark and Kafka and other types of technologies that are out there, and GPUs to be able to handle this at speed. And frankly, being able to combine and be able to plug into actually the places where people are using it, such as workflows. And so just talk a little bit about what we're doing at Lumiata as sort of an example of how we can sort of unpack AI for healthcare to really handle that complexity of health data. We fundamentally want to change the way health data is being put to work. We want to say, how is it I can put every single ounce of your data, from your social to your health data to otherwise, so I can predict with the greatest degree of accuracy where you are today and how that's evolving, and really bring around that clarity and subsequently being able to allow us the management and control that we're all really looking for in our lives, especially with healthcare. And so that's what we do. We're basically building medical AI to precisely predict and manage an individual's risk and subsequently their health, and to really enable the automation that we're looking for. If you think of us as a team, we're actually really data scientists, clinicians, where we have basically people sitting side by side to really understand the data, to really make sense of it, and really be able to apply it in a way that makes sense and of value. We've now dealt with over 60 million patient records, about 175 patient record years. We spent about 40,000 physician hours curating that and basically analyzing all PubMed, which is about 50 million articles, which ends up being about 3+ terabytes of data. And really the idea is to be able to predict at that individual level across multiple different conditions or events how that risk is today and how that risk is evolving. It's what we call the risk matrix. And we leverage what we call the medical graph, which is basically our understanding how does actually everything connect. Think of that digital version of medical science and be able to apply that in real time so that given any new piece of data, 100 milliseconds later, I can go ahead and tell you, here's the best way I understand where this person is going and what's going to work for them. And that's really the idea, to be able to capture the value of data. And many organizations, especially in healthcare, amongst all, data sits there, but is actually not being applied to work, as per my very original question. And really the idea is, how do we create automation so we get scale? Because fundamentally in healthcare, it's a scale problem. And so by really alleviating people of efforts to where basically we can have machines do it, people can spend time doing what they care about in healthcare, which is focusing and actually caring for other people. And so fundamentally, we go ahead and understand how all this actually connects to each other. It's not like day 2 of being hypertensive, you have a 1.2 odds ratio of chronic kidney disease. It's really over a span of 10 years, sort of an S-shaped curve, and that modulates by age and gender. And really what this allows us to do is generate very personalized predictions at the individual level so that we can go ahead and make sense of it. So, and that fundamentally allows us to start dealing with the dimensionality, understanding how things actually potentially aggregate, understanding how to make sense of all the multiple different coding systems that are there in healthcare. Being able to do this in a way that's systematic and at scale allows us to go ahead and make use of this data. And really, as I said, with our risk matrix, it's not just being able to predict, but it's also being able to be interpretable. How we can actually show you the chain of medical reasoning as to why. And beyond the issue of being able to create trust within the healthcare community, within us as individuals, because if anyone gives me a suggestion, always my first question is why. But beyond that, it also gives us the ability to understanding what to do. How do I address it? If I can start understanding what are the true determinant factors for someone's risk, I can be very targeted in how I take action to help minimize those risks and help them live the best life possible, and be able to show all that chain of reasoning all the way down to PubMed references and otherwise. So at a very broad view, we take lots of raw data, leverage large amounts of things like Spark, GPUs, and other things to really convert that to a very structured, standardized form, and then be able to predict at scale what's going on. And really a pipeline to develop and scale medicine, where it's all about the issues of deep learning. We can go into it. I only have a few minutes here, but how do you create the feature vectors for somebody, for a particular disease? How do you actually understand what are the relevant features that are relevant for this person or for this disease in specific? How do I combine multiple things? How do I, in fact, take it to school by leveraging things like autoencoders and vector embeddings? These are all things now with the power of GPUs. We can actually train models literally minute by minute. We can go over millions of people with the distributed cluster and actually train models. And so therefore, really being able to have mass amounts of iterations and being able to understand what features are relevant, have huge amounts of testing of looking at mutual information and otherwise to really understand what feature vectors make sense, and really being able to do so and process it at speed so that it can be used interactively with people across the world. And really the idea is, I'm sure many of you are familiar with many of the technologies, Spark, Kafka, TensorFlow serving, and things of that nature. And really it's about building that virtuous cycle. As we get more data, as we get more use, we're able to go ahead and predict sharper and sharper, and therefore derive more and more value. And really, once again, this is where a lot of, we happily use a lot of NVIDIA GPUs, but also, a lot of processing power otherwise. And really it's about taking that data to action, because people want to know what can they do to help someone in their health. What is a diagnosis someone has that people have not yet identified so that they can go ahead and actually help that person live a better life. And really it's about doing that automated risk stratification, helping reduce costs by enabling automation, enabling you to be able to communicate effectively between people who are bearing risk and people who are delivering care by being able to have interpretable models and moving forward from there. We've done this with APIs and otherwise, and we've done this for a variety of different things, such as large-scale health insurance companies, where we've analyzed over 850,000 members, helping identify what diagnoses are being missed and therefore what they can do about it. Helping large ACOs with hundreds of thousands of members and over 1,000 plus users using the system every day to understand who they need to be engaging with, why they need to be engaging with, and what's going to actually benefit for those patients. And really being able to do differential diagnosis and power and understanding of therefore what level of care do people need to do. So really being able to amass and take this data and be able to apply it in everyday world situations that are there in healthcare, but really being able to make use of it and help people drive care. The whole idea, once again, is we have this notion of through AI, can we make health human again? Can we give people that control? Can we give people that ability to manage their health? And we do so in ability by being able to predict very accurately how an individual's health is today and how that's evolving. So really across the board helping people. And really powering clear, predictable health outcomes. So quick round of what we do at Lumiata and how we engage deep learning and AI to really transform healthcare. Thank you, everybody. Appreciate it.